Problem 2.6. A coin has been bent in such a way that it comes up heads not half the time but 80% of the time. This bent coin is placed in a box, and the box also has some fair coins. A friend selects one coin and tosses it 20 times. So there are two possibilities. The null hypothesis is that the coin is fair, and the alternative hypothesis is that the coin is bent. So we'll choose the following decision rule. We'll reject the null hypothesis if the coin comes up heads 18 times, and we retain the null hypothesis otherwise. So the picture kind of looks like this. We have our rejection region. Here's 18, 19, and 20. And if it's any of those values, for these we reject. But for anything less than those numbers, 17, 16, and so on this side, we retain. At this extreme. Okay, so the first question is to determine the value of alpha. So notice this is a slightly different wording than most of the questions in this that involve hypothesis testing. Here, the decision rule is stated, and we have to figure out what the value of alpha is for this decision rule. For most problems that we've seen in this class, alpha was specified. But this time, the rejection region is given to you, and we need to figure out the value of alpha. All right, alpha is the probability of a type 1 error. A type 1 error happens when we reject the null hypothesis, even though the null hypothesis is true. So in this problem, that would mean that I reject the null hypothesis. I have a count of at least a size 18, even though it's a fair coin, and the chance of getting ahead is 50-50. Okay, now this is the chance that k is greater than or equal to 18. So to make this computation, I need to figure out the chance that 1 minus the chance that k is less than or equal to 17. Using either Microsoft Excel or else using a TI calculator, the entry that gets returned is going to be always corresponding to something that you get for plugging in less than or equal to. So the value of alpha is going to be equal to 1 minus binom dist 1720.5 true. An analogous command would work on a calculator. And so we get a value of alpha that is indeed quite small, about 0.0002. So that is a very small value of alpha. Now let's figure out what beta is. Let's figure out the probability of a type 2 error. So the probability of a type 2 error is beta. And a type 2 error occurs when we retain the null hypothesis when it should have been rejected, and the alternate is true. So in our problem, that's the chance that k is less than or equal to 17 if pi is 0.8. That it is the bent coin. Okay, now this we can directly compute without this 1 minus business because it's already a less than sign. So binom dist. We have 17 successes, 20 trials, but this time the probability of success is assumed to be 0.8 as opposed to 0.5. So the difference between the previous computation and this one is that the pi value is 0.8 as opposed to 0.5. Once again, an analogous computation could be done using a TI calculator. And so we get 0.794. So there's a very high probability of making a type 2 error if the alternate is true. So this is typically what happens in real life experiments. If the value of alpha is very, very small, then that drives up the value of beta. And increasing the value of alpha will bring down the value of beta. So typically in experiment, alpha is chosen to be some level of comfort that we already know, like 1% or 5% or 0.1%, and then the value of beta is computed to match it.